Hello, everyone, and welcome finally to the second session of the meeting. As most of you know, we had a little mix-up in the schedule, so Peter McCulloch is going to give his talk starting 1 hour from now at, I've again forgotten, but at 5 o'clock UTC. But now we have in the scheduled slot the scheduled talk by Malte Gerhold from the University of Greifswald, and he's going to talk about independence and Lévy processes in monoidal categories. But before starting, Malte, can you just tell us your policy with regard to questions so that we're all aware? So would you like to have questions during the talk?
Yes, please interrupt whenever you think it is necessary to stop me.
So if you have questions, please send them via the chat. I shall be monitoring the chat, and we can interrupt. Okay, so thank you very much, Malte, and please go ahead with your talk.
Yes, thank you for the introduction, and thank you, Tobias, for the invitation and all the organizers for making this possible. Okay, so let me just give you a short overview what I'm going to talk about in the next 45 minutes. So after some short motivation why I like to look at these things, we will talk about independence, and not only stochastic independence, but we really want to kind of get the idea what independence in several contexts means and how all of this can be captured by one idea that connects to monoidal categories. Okay, then I will tell you something about my background about non-commutative probability, which is why I started to look at these things, and then I come to the results I want to present about inductive limits that connect all of this to Lévy processes in the end. Okay, so let's start with some motivation. In classical probability, there's a correspondence between Lévy processes. So what are Lévy processes? That are stochastic processes whose increments, so they have values in a group, let's say they are real valued, and the increments of the process are stationary and independent over disjoint intervals of time. And these can be described up to equivalence by the convolution semigroup of their one-dimensional marginal distributions. And on the one hand, okay, if you have a Lévy process, you can just look at its distribution at a given time, and that gives you this convolution semigroup. And on the other hand, there's a canonical way to reconstruct the process from the convolution semigroup via the Daniel-Kolmogorov theorem. So let's look how this works. So one thing I already said, if you have a Lévy process, random variables indexed by the positive reals, stationarity means that the distributions of the increments down here, I hope you see my my mouse also where I show. I'm not sure about this though. Can you see it? Where my mouse is?
Yes.
Yes.
Yes. Okay.
Yeah.
Okay. Great. So stationarity means it doesn't depend. This distribution doesn't depend on S, only on T. So you can go back, and it's easy to see that these distributions form a convolution semigroup. That is, if you take the distribution of time S and convolve it with the distribution of time T, you will get the distribution of time S plus T. And on the other hand, you can form a projective limit of this projective system, where you take the finite dimensional distributions on Rn, given just by the product measure of mu T1 up to mu Tn. These form a projective system in a canonical way, and then you can take the projective limit and take these xt just as the canonical projection onto the one-dimensional representations. Okay, the one-dimensional distributions. And this projective limit always exists by the Daniel-Kolmogorov theorem, because this is a projective family of measures. Okay, and I told you I come from non-commutative probability. Let me just very, very briefly say what I mean with this for now. It's the theory of states on unital star algebras. And why do we call this probability? Well, it's a generalization of probability, because if you have a probability space and you form the space of a bounded measurable function, L infinity, that is a star algebra. Of course, a commutative one, because the product of functions is a commutative product. And there is also a state on this. Well, a state is just a positive linear functional which takes the unit to the unit. And that's, of course, just the expectation or the integral. Okay, so if you integrate the constant function 1, you will get 1. That's that is being a probability measure. So, and this setup you can try to generalize to non-commutative algebras and try to use your probabilistic intuition to formulate theorems that you would like to prove and see how it works. And independence is a very interesting point now, because you can generalize independence to such a non-commutative situation, but not uniquely. So there are several meaningful generalizations of stochastic independence. And because of that, we would like to have a general framework also for this correspondence between convolution semigroups and Lévy processes, or not here I wrote it more concretely, independent increment processes, that works in all these situations and for all different kinds of independence that one can think of. So just to give you an idea right from the start why there are different notions of independence, maybe a good thing is to think about random matrices. So if you have a random matrix whose entries are independent in the usual sense, and if you have two large such matrices, then you could assume that these matrices also should fulfill as matrices with a matrix product some form of independence. But it cannot be the classical stochastic independence, because the product of matrices is not commutative. And this leads to the notion of freeness. I think free probability was mentioned once already today. Okay, so you see in non-commutative situations, it's not clear what independence means, and there are more than one meaningful generalization of stochastic independence. Okay, so, but now let's take a step back and not think about necessarily stochastic independence, but just about independence. What is independence? The first notion of independence that we learn about in mathematics maybe is linear independence. So here I wrote, when vectors in a vector space are called independent. And I want to convince you that many sorts of independence that we know kind of have a common scheme they follow. So we can define independence not only for vectors, but for subspaces. And one way to put it, when subspaces are independent, is when the canonical map from the direct sum of the subspaces into the larger containing space, which just sums up all your vectors, when that is injective. This is not this is quite easy to show, but one just has to think about it a little bit. This is just the characterization that these subspaces don't have any non-zero intersection. Okay, and then we can say vectors are linearly independent if the subspaces they span are linearly independent. Nice and easy. So the same works for algebraic independence. So if you have elements of a field, let's say LB, A and B are elements in a field, and they are algebraically independent over some field K, then then that means that the only polynomial which vanishes at the point AB is the zero polynomial. And again, we can translate this into this time into subalgebras. So we say that unital subalgebras of a larger containing algebra are in tensor position if the multiplication map, which extends to a linear map from the tensor product, is injective. Again, this is not difficult to show that that if you have two transcendental elements in the larger field L, they are algebraically independent over K if the generated algebras K of A and K of B are in tensor position. And finally, let's come to stochastic independence. We say that events in a sigma algebra are independent if the probability of their intersection is the product of the probabilities. And we can also extend this to subalgebras, to sigma subalgebras, E and F of sigma. And we have this map, which is like a product map actually, which sends two subsets to their intersection. So if you think in terms of their indicator functions, this is very similar to the situation before, that you multiply these two functions. And this should fulfill a certain relation now. It doesn't have to be injective as before, but it has to fulfill this relation, how the probability of an intersection is related to the product measure of the restrictions, okay? That it is just the product measure. And of course, events are independent if and only if the generated sigma algebras are independent. So what did we observe here? So kind of sometimes we want to talk about independence of vectors, of elements, maybe of events, whatever, but we always could formulate it in such a way that it's about some sort of sub-objects. Okay, this is good. So we already connect to something categorical, although I don't mean sub-objects now in a strict categorical sense, as we will see soon. And in all the situations, there was a categorical tensor product. So there was some monoidal category around. In the vector space setting, this was the direct sum of vector spaces. In the algebra setting, it was the tensor product of commutative algebras. And in the stochastic independence setting, it was the product measure of probability measures. And the factors were always canonically embedded into this product, okay, like the direct summons into the direct sum, or the sub-sigma algebras into the larger sigma, into the product sigma algebra. And independence of sub-objects always looked the same. There was a canonical, in these cases, morphism from the tensor product to some common object A, which fulfilled some certain additional requirement. Twice it was injectivity, and once it was something else, some compatibility with the probability measures. Okay, so it always looks like this. You have some way to interpret B1 and B2 as sub-objects of A. And then you have the tensor product, and they are independent if there is this independence morphism H. Okay, and this we want to take now as a definition. So we now formulate our categorical setup. We say that the monoidal category has compatible inclusions if there are two natural transformations from the projection onto the first component to the tensor product and the projection onto the second component to the tensor product, which are coherent. So when you, in particular, I mean, if you iterate these to, let's say, embed the third object into the tensor product of 7 objects, then you can do this by some iteration of iota 1 and iota 2, and it shouldn't depend how you do this. Okay, and of course it should also be coherent with the structure of the monoidal category, with the associators and the yeah, and the isomorphisms with the unit object. And then there's a theorem. Maybe this is well known. I don't know, but let's just state it. So this coherence is equivalent to having a semi-cocartesian category, which means that the unit object of the monoidal category is the initial object, and you have this minimum coherence requirement that your inclusions jota 1 and jota 2 are obtained from tensoring with this unit object and then embedding the unit object via the unique morphism into B. Okay, and I have to thank Tobias at this point, who told me about this, that Cartesian categories, semi-Cartesian categories exist under this name, and that these things are probably known to many people in category theory. Okay, and now we can define if we have morphisms from Bi to some common object A. Then we say that they are independent if there is such an independence morphism H such that this diagram commutes. This definition, I think the first one who came up with it was Uwe Franz in 2006, and he defined it only for 2 morphisms. And because he did not yet have this look at this compatibility of the inclusions and these semi-cocartesian categories, then this is the most you can do. But in this setup that I just presented, there's no problem taking the same definition for any number of independence morphisms. You just write the tensor product of any number you want and take the correct inclusion, and you want 1 independence morphism such that everything commutes there. Okay, now let me tell you a bit about. Yes, please.
What is an independence morphism? Does it have to be monic?
No, no. We don't assume anything about it for now. It's just any morphism which makes this diagram commute. In many examples, if it exists, it's unique, but we do not require that. So it is possible that there is more than 1 independence morphism around. Okay, so let's look at non-commutative probability in a bit more detail. So we define what the non-commutative probability space is, and this is a unital star algebra with a state. So state meant you have a positive linear functional which takes the unit of A to the unit in the complex numbers. Okay, and a random variable is now just a star homomorphism from some other star algebra B to this probability space A. Note that the direction is reversed when you compare it to probability spaces and random variables, because we are talking here about the algebra. So you should think of B as the algebra of functions on the probability space, for example, like the L infinity, and then of course the arrows all go into the other direction. So J is more like X inverse for a random variable X. Okay.
There's a question from Joshua Mayers. I don't know if he'd like
Yes.
to unmute and ask it himself.
Sorry, I didn't know whether it was okay to follow up, so I just put it in the chat.
Would you like to ask the question?
You say, yes, you're completely right. That's a very good point. So the point, if you think about the direct sum example, the point is that you restrict the morphisms. So I should have said that. So if you say that your category is the vector space and the morphisms are only the injective linear maps, then this gives you the right notion of independence. So the existence of a linear map such that everything commutes is not the problem there. It always exists, it's just the sum. But the point is whether it's a morphism in a certain category or not. So this time in the category of vector spaces with monomorphisms.
I see.
Okay.
So in
So
general,
and in the same in the algebra example, and a little bit different in the stochastic independence example. There you would take the measure preserving measurable maps as morphisms.
Okay. Thank you.
Okay. Thank you for the question. Very good. Very good that you interrupt. Okay, so about non-commutative probability. So just have to keep in mind that the arrows are reversed, and this is why in all what follows, I will have the arrows reversed to the intuition you maybe have when you think about probability spaces. Okay, then there's some things I want to go over quite quickly. So we do not assume this algebra B to be unital, but we will make use of its unitization. So you can just make an artificial unit and adjoin it to B. And this is what all these twiddles mean. Just to really make it a state on some unital star algebra, then you can compose this twiddled one with the state on A to get something which we call the distribution of the random variable. And if you translate this to the probability setting, it makes a lot of sense. Although in this purely algebraic setting, one has to be careful that the term distribution does not have any analytic meaning. So if, for example, you take a random variable which is given by an element of A in the following sense. So if you have an element of A, you can form a morphism on which is defined on the polynomial algebra. This 0 means you don't have a constant term yet, just x and x squared and the span of this. And map this indeterminate x to A. This gives you a homomorphism, so a random variable. But then the distribution is really just a collection of moments. It doesn't mean that there is a probability measure. The moment problem can be quite difficult. So maybe you don't know if this sequence of moments is actually the sequence of moments of a probability measure. So there's not any. We call it the distribution, but there's no analytic implications of that. Okay, another example of random variables are subalgebras, which you just embed, and then you also have such a star homomorphism. Okay, and now we form our category of non-commutative distributions. The objects are pairs where you have a star algebra and a state on the unitalization of this B. And morphisms are star homomorphisms, which translate one state into the other. Okay, and some observations. So every object in NC Dist is the distribution of such a homomorphism, namely just the canonical embedding of B into its unitization. And every morphism in this category can be seen as a random variable with distribution given by phi1. And if you have your non-commutative probability space, you can also see it as an object in this category. You just have to put one artificial unit on top and extend your state, which is then automatically again a state. So everything we need can be formulated in this category. And now the question is this a monoidal category? And the point is in many ways. So this is the one key observation of non-commutative probability, that there are several meaningful ways to turn this category into a semi-cocartesian category. And every different choice of tensor product will give you a different notion of independence. So, and we call such a tensor product a universal product if it fulfills the slight extra assumption that if you take two objects and take the tensor product, then you should get the free product of the algebras as the algebra on which the product state lives. But by universal, so the free product is the co-product in the category of algebras. So by the universal property, if you have a more general tensor product which makes NC Dist into the semi-cocartesian category, it will always be related to one of these universal products in a simple way. And then there's a classification of such universal products, so which is attributed to Muraki usually, but some important previous results are due to Van Gogh and Schürmann, which go from this more categorical definition to something more concrete. Okay, I don't want to go into the details here. We want to talk about other things. Okay, so if it was only for these 5 universal products, maybe we wouldn't have started to build up this categorical framework to study things. Although also for these 5, it's already maybe fruitful because, and this is also what Uwe Franz, when he invented this notion of independence, did. He wanted to compare the different notions of independence, and this results in looking at monoidal functors between the categories with different products. Okay, but what's more, if you take slight variants of this category, then you will get also a lot more examples. So it's good to what things that you want to do in this non-commutative probability independence world, you should try to do it for everything at once, because there are a lot of examples, and it's nice to know if you can treat them all simultaneously. Okay, here are some examples. I don't want to go into much detail, just explain you roughly how to read this. So the free product of algebras is spanned by words whose letters come from the 2 algebras, and which are alternating. So for example, the C1 could be in algebra 1, then C2 in algebra 2, and so on, alternating. And then you can, one thing you could do is you multiply everything that's in the first algebra and plug it into the first state, and multiply everything that's in the second algebra and plug it into the second state. But now you see you have other options. Because of this alternating structure, you can kind of take the individual factors C1 to Cm, and for example, you could just evaluate everything 1 by 1 and just multiply the results, or you could do something more fancy. Okay, so there are these other examples, and then the definition of independence, if you have such a universal product, is that the joint distribution is this product of the marginal distributions. And we can now formulate this in the categorical language before. So they are independent if this unique morphism, which exists by the universal property of the free product of algebras, which maps the free product of the VIs into A, if this is an independence morphism, that is, if it is a morphism, that is, if it has gives you the correct relation between the states. Okay, if it translates the one state into the other. Okay.
I have a small question.
Please.
If you're working with finite dimensional star algebras, is the tensor product, the ordinary tensor product is not an example of such a thing, right?
Almost. It's almost. So the ordinary tensor product is very closely related to this tensor product. Yeah, but I don't want to go into the details now. But in principle, yes. But technically speaking, no.
Okay.
But
so,
yeah.
Okay, because I was mainly curious about the case of like 2 density matrices or something like that, if it reproduces the usual notion of independence there.
Yes, it produces the usual notion of independence if you take this product on this but then this free product construction is unnecessarily large. So
Okay.
if you're just interested in the tensor product, you could do with a simpler algebra.
Mhm.
Then you could take the tensor product of the algebras also. So
Okay.
if you're just interested in tensor product, this is a kind of blowing things up unnecessarily. But for all the other examples, you need it.
Okay, thank you.
Yeah, sure. Okay. So this is now, if this was not interesting, don't worry. You can almost forget about it now, because everything we do now is just in this categorical setup. But I just wanted to advertise this non-commutative probability and tell you also why I'm interested in these constructions. Okay, so let's look at the inductive limits. So first of all, in the beginning, we said that we want to generalize this Daniel-Kolmogorov projective limit construction. Now we have inductive limits because all our categories are kind of have their arrows in the opposite direction. So this is really just the same thing, but we just like to think of going the arrows following the direction of the algebras and not of the spaces. And why do I have two inductive limits? Because there are some other applications also, which I did not yet talk about, where it's kind of good to have this. So the first and the second together correspond to the projective limit of this reconstruction of the Lévy process from its convolution semigroup. But it's good to split it into two parts, because the first works in some situations, the second works in other situations. So let's see what I mean here. Okay. Yeah, so to talk about this, we invented the term, which is maybe not necessary, but this is maybe up to discussion. So something we call Comonoidal Systems in a category over some monoid. So M is a monoid, C is a category, a monoidal category. And it consists of some objects. The index is always from the monoid, so T is in M. The objects are in C. And then you have morphisms, which we call co-multiplications from the object corresponding to S plus T. So I always write this monoid additively, although strictly speaking, we don't need it to be commutative at this point. But most examples, interesting examples, are commutative. So let's just stick with the plus. And you have a co-unit morphism from the A0 to the unit object of the monoidal category. And they should fulfill these properties, co-associativity. So if you split R plus S plus T into the R and S and T, then you have two ways to do this as a, yes, graded comonoid, right? So thank you. So this probably is known to everybody here as graded comonoid, and but to call it like this was kind of confusing to us, because we work a lot with graded coalgebras, and coalgebras are the comonoids in the category of vector spaces, but a graded coalgebra is not the same thing as this, because there are some subtleties how to put all these delta STs together. If you come from this coalgebra, algebra by algebra world, then you would say that the graded coalgebra has one co-multiplication. But how can you build all of these things together if there are maybe uncountably many indices? So had a short discussion some years ago with Tobias about exactly this point. So I guess in category theory, this is just a graded comonoid. But the terminology confused us, I must admit. So probably we should change it still. But another way to put it, what it is, it's a colax monoidal functor from the monoid into the monoidal category. And we call this comonoidal system, or the graded Comonoid full, if and only if this is not just a colex monoidal functor, but a strong monoidal functor. That is, if all these maps are isomorphisms. Okay.
Sorry, one very small
Yes.
question.
Yeah.
In the case of algebras, delta is a star homomorphism from an algebra
Yes.
into C?
The large the big delta is a star homomorphism from
The smaller one.
A
Sorry.
S plus T into the tensor product or the free product, depending on the category.
Sorry, yeah, the smaller one I meant actually. Lowercase
The smaller
delta.
one, yeah, it goes into the complex numbers. Then it's just a just a character.
I mean, I guess I'm not familiar with many examples. I mean, if I take M by M matrices, I don't
then
have
it
any.
doesn't exist.
Right. Oh, okay, good.
Right.
Glad
Then
we
it
know.
doesn't exist. Yes. Right. Yeah, you're completely right. Yes. So the M by N matrices don't have a character, but many algebras do. Right. Okay. So, for example, if you have group algebras or something, you have characters. So, okay. Right. So this is full and strong, and then I want to emphasize that convolution semigroups are a special case of this. So if you have in the you can build this semi-cocartesian category of distributions. So the objects are probability spaces, and the morphisms are measurable functions. Where here I now to get this I reversed the direction. So F is a morphism from omega 1 to omega 2 if it's a map from omega 2 to omega 1. And the product of probability measures gives you this tensor product, and the unit object is just the is just the 1-point probability space. Then convolution semigroups are really comonoidal systems. So if you have a convolution semigroup, you can form the distributions. AT is just the real numbers with the Borel sets and your measure mu t. As this delta st, you take the sum operation, and then if you want to know if this delta st is actually a morphism from as plus t to as tensor at, then this amounts to the same thing as saying that mu s plus t is the convolution, because the convolution is what you get by the pullback of the sum. Okay, it's the image measure under taking the sum. Okay, and also this co-unit, this delta, this is a morphism if and only if the distribution at time 0 is the Dirac measure at 0. Okay, so we're really formulating something which generalizes convolution semigroups, and I want to go very quickly through this slide and just tell you that in these algebraic setups of star bialgebras or something called dual semigroups, where you have a co-multiplication which maps into the free product of an object with itself. So these dual semigroups are comonoids in the category of algebras. In both these cases, you can formulate what the convolution semigroup is, and in both cases, you can identify them as comonoidal systems or graded comonoids in the category of noncommutative distributions. Okay, let's not go into detail here, but now let's look at these inductive limits. So the first inductive limit works like this. If you have a fixed time t, you can try to decompose it as a sum of any number of smaller times. So let's say t is an r plus now. These are really just, you direct them by refinement. And then you get the natural structure of an inductive system here, where a tau is just this tensor product of the ATs for all for this splitting T into the sum. And if your tensor product preserves inductive limits, you can show that the inductive limit you get from this inductive system forms a full comonoidal system. So it corresponds to a strong monoidal functor from R plus into your category. So let's quickly go through what all this means. So how is it directed? So you say if that sigma is larger than T, if each of the Ti's splits into the sum of the Si's, and then this is an inductive system, because if you insert one co-multiplication here at the point, this shows you how you move to a one-step refinement. So if just Tk is split into R and S, then this is how you build your map delta tau sigma, and then you can do a short calculation that this iterates with the right associativity conditions so that you really get an inductive system. And yeah, I already said that full means that all these structure maps are isomorphisms. So this is the first inductive limit, and this was shown in the category of Hilbert spaces, but actually the proof doesn't depend on in which category you work. But there, these things are known as subproduct systems and product systems. And this was Bhatt and Mukherjee in 2010. And now we want to go to Lévy processes. So the second inductive limit, in the first one, we fixed the T. And now we assume that we already have a full comonoidal systems. And now we need these compatible inclusions, or these semi-cocartesian categories, to form the inductive limit where we let the T go to infinity. So, and how can we embed AS into AT if S is smaller than T? Well, you can just take your canonical, your inclusion given in this category as the first factor of the tensor product, and then use the inverse of this co-multiplication to multiply them together to give you something in AT. And now, for time reasons, I will not look too long at this diagram, but this is basically coherence, naturality of the inclusions, and here in the end, the co-associativity of this map delta tilde. Okay, so it's simple diagram chase. Now, what do we call a categorical Lévy process? It should be some sort of process. So it should be morphisms mapping your objects into some common object A. So the AT should now be a comonoidal system because they should correspond to this convolution semigroup of distributions. And then the stationarity means that the increment from S to T should only depend on the time difference, on T minus S. So this encodes stationarity. So this is like the convolution semigroup, and this is like the probability space. Then you have that over disjoint times interval, these morphisms should be independent, and they should be built together. So you should get JRT out of JRS and JST. And how does this work? It should work via an independence morphism. So you want that there exists an independence morphism for these two, such that if you compose it with the co-multiplication, you get the increment over the larger interval. Okay, and then the theorem is that the JSTs that you canonically get from AT minus S into A infinity from a comonoidal system by first making the first inductive limit, then embedding this as the second factor in the tensor product, then multiplying together with the inverse of the co-multiplication, and then embedding with the second inductive limit into A infinity, that this fulfills these properties of a categorical Lévy process. And here's how the proof roughly works. So you just write down the independence morphism and do a diagram chase, which I will not do now. Okay, and then you can also think about what is really needed in each of these steps. So for the first inductive limit, we don't need that M is commutative, but what we need is it's the so-called unique factorization monoid. So this is what really leads to getting an inductive system there, that you don't, all ways to split something as a product should be comparable. Okay, then, yeah, that when you want that your first inductive limit gives you a full comonoidal system, you need that the tensor product preserves inductive limits. And for the second inductive limit to give you a categorical Lévy process, you need these semi-cocartesian categories or compatible inclusions. And there you really need an abelian monoid without non-zero invertible elements. Okay, that's what I wanted to tell you. Thank you for your attention.
Okay, so thank you very much. That's very, very good timing. So I suggest we can either clap, you can either unmute, or under the reactions button, you can find a little clap icon which you can click on. I'm unmuted, so I'm going to clap like this. And are there any questions for Malte?
I have a very basic question. Can you give me an example of a Lévy process in the non-commutative setting? Just something that I can think about, so that, you know,
yes, so it, do you know, for example, symmetric Fock space from physics, or boson Fock space? Yeah. So there you could take the process of creation operator. So if you take the boson Fock space over the L2 of the half line of R plus, and then a Lévy process would be given by the creation operators for the indicator function of interval from 0 to t. So this would be a very canonical example of a quantum Lévy process or non-commutative Lévy process.
Yeah, for some reason,
yeah. Sorry?
Well, I guess I don't totally understand what that means, but
yes, okay.
I think of like creation annihilation of particles, or am I like selecting a range, like an energy range in which I'm creating these particles?
Yes. Well. Okay, I see.
But maybe we could do the question session here as sort of getting food for thought, and then more technical discussion could go to Zulip. I mean, we could come back to it, but maybe just see if there are other questions.
Yeah, maybe it's better to write something down. I think just talking is. No.
I suppose it's nice to get a suggestion of the answer, but I think more technical discussion can perhaps go to Zulip, because there might be other questions. Are there other questions for Malte?
I have a question.
Yeah.
So at some point fairly early on, you talked about the fact that defining independence in non-commutative contexts, such as matrix multiplication, is difficult. Do you know what I'm talking about?
Yes.
Yep. Can you expand on that? Why is it that the non-commutativity causes a problem?
Well, it's I don't know if it's really causing the problem, but at least it cannot. You cannot capture it with the classical concept of independence, because if you say classically random variables are independent, then you want to think of them as real valued functions which are commuting. And you also want to say that the distribution is the product measure. All this doesn't, if you try to translate this to matrices, you cannot, if two matrices don't commute, there's no way to interpret them as functions on the same space, and to interpret the matrix multiplication as a multiplication of functions, because multiplication of functions is always commutative and the matrix multiplication is not. So you have to do something else. Yeah, I don't know. Did this answer the question, or? Well,
maybe I'm being slow. I don't really get it. If you can, I mean, I've had some contact with free probability
Yes.
before, and so I think I sort of understand roughly what's going on, but I've never quite got why, I guess, what the interaction is between non-commutativity and this different handling of independence. But maybe, I mean, I don't want to monopolize.
So maybe
you can point me to a reference.
Maybe
perhaps,
it gets clearer if one goes does it more concretely. So what is the state? What is the state on an algebra of matrices? You usually take the normalized trace. Okay. So you have to come up with something. So you have a probability measure, which gives you the distribution of the entries of the matrix, right? So you say the entries of the matrix are sampled independently, let's say with the normal distribution, with Gaussian distribution or something. Now you have two large random matrices, and you can want to know something, for example, about their eigenvalues, the distribution of their eigenvalues. Then what do you do, or what you can do other things, but what you can do is to look at the moments in the state given by the normalized trace. So you look at the trace of the matrix, you look at the trace of its square, you look at the trace of its third power. And if you collect all these moments, you can say something about the distribution of the eigenvalues. But now this is really taking this normalized trace. If you have two random variables, they typically don't commute. So in which sense would you say that these two matrices are independent with respect to the trace? So this is the kind of the dilemma you're in. Your state is given by the trace. This is what helps you to determine eigenvalues. And these two matrices have some sort of general position or something to each other. But they are not commuting. So it's not like the trace of A times B is the trace of A times the trace of B. This is just, well, this is even correct, but if you take longer products, so trace of A, B, A, then it's, what is it? It's not just trace of A squared times trace of B.
Yeah. Okay, I see where you're coming from. Thank you.
Yeah. Thank you.
Other questions? Okay, well, I have a simple question about again, about the early part. So when you defined independence, you had this independence morphism, and you said you don't require it to be unique.
Yeah.
Presumably, so in some of your non-commutative examples, then it is essential that it's not unique. Is that the case?
No. In the real examples that we have in mind, it is usually unique, because let me go to that slide.
So even in
the universal products,
even in free probability,
even in free probability, because here we use this free product. So if you want any algebra homomorphism from the product of algebras to another algebra, which restricts to given morphisms from B1 and B2, it's always unique. So the only question is whether it fulfills this extra requirement concerning the distributions and the states. So, but for one, it's not really. It's not the uniqueness is not really needed. So we didn't want to put it. But we don't have convincing examples, I think, where it is non-unique, because most examples that one has are built in such a way that the co-product in a certain category is involved. So there is only one candidate for a morphism, and either this is a morphism or it is not.
Yeah. Okay. Well, that's interesting. So, I mean, I worked on something relative similar to some of the first part on independence a while ago, and I had a generalization to conditional independence that required a fibered monoidal structure. And for that, it was really essential to have the uniqueness of this independence morphism. So maybe we can discuss it. Maybe we can discuss this offline. But I know that conditional independence is something that's difficult in free probability theory. And
Yes.
I had been wondering if that was related to needing that non-uniqueness in this case, but given that you have uniqueness, that makes me more curious about the situation. So anyway, I think this is also something to take into discussion offline. Also, because time is pressing. So we have, I'll just see if there are any quick questions. Okay, so
one question, but a comment. I was also actually very interested in the setting of if you had like a notion of conditional independence in this framework as well.
okay,
Yes,
well,
so,
maybe we can take that to Zula.
Okay.
Sorry, I didn't want to stop you from answering. Maybe we do still have 5 minutes till the next talk. So if you've got a quick thing to say about that.
So the usual way, I guess, to go about conditional independence is to take a different tensor category where it is again this form of independence. So you usually would take amalgamated free products. So you have a common subalgebra, which is what you condition on, and then you take the free product where you identify this subalgebra in the two.
Yeah. Okay, good. So thank you very much, Malte, for that very interesting talk. So let's have another little clap, either physically or with the clap icon. Maybe I shall clap with the clap icon this time.